All right, today we're diving into a search for what comes after quantum computing, a new era for AI called Phase N. This whole vision comes from a work by Anthony Piper, and it suggests a totally new way to build intelligent systems, literally from the ground up.
So what's the core idea here? Well, it's all built on this one powerful concept, using evolution, mutation and selection, to discover entirely new ways of computing. We're talking about moving past the simple ones and zeros we use today and even beyond the wild states of qubits into completely new territory.
To really get what's going on, we need to look at the core components. You can think of these as the fundamental materials the architect, in this case, Anthony Piper, is using to build this whole new computational world.
First up is something called a multi-value logic DSL, or domain-specific language. Now, instead of being stuck with a simple on-off or maybe a -1, 0, +1 system, this tool lets the computer literally invent its own logic systems. For instance, it could come up with a golden quaternary logic that's based on the golden ratio, which makes it way richer and more flexible than what we have now.
Now this next piece, this is a huge departure from traditional quantum computing. Instead of using a fixed set of gates to do things, this system uses what are called gateless operators. Imagine a sculptor who can just shape clay directly with their hands, instead of being limited to a handful of specific tools. That's the idea here. It gives you much more fluid and stable control over the system's state.
So how do you steer this new kind of system? With a really clever computational shortcut. It uses a matrix-free quantum Fourier transform accumulator. What that means, in simple terms, is that it lets the system aim for a quantum-like target state without the absolutely insane computational cost of building the gigantic matrices you'd normally need. It's all about making this practical.
And here we have another key innovation, weight harmonic encoding, or WHE. You know how today's AI models rely on these massive, power-guzzling matrices of numbers? Well, WHE replaces them with a super compact layer of resonant frequencies. Think of it like storing a ton of information in a complex musical chord instead of a giant spreadsheet. It's just a more elegant, efficient, and evolvable way to do things.
Okay, so we've got the building blocks, but how does the system actually evolve a solution? It all comes down to the genetic code, the DNA, if you will, that defines each potential AI.
So the genome for each of these candidates is defined by these 4 key sets of genes. Evolution gets to play with everything: the number of logic levels it uses, the specific properties of that harmonic layer, the exact sequence it uses its operators in, and even the learning parameters for its own internal brain. All of these get mutated and selected over thousands of generations.
Of course, for evolution to work, you've got to have a goal, right? You need some way to measure what good is. So, what does a successful, evolved system actually look like in this world? Performance gets measured across these 5 critical areas you see on the chart. The system gets a score on things like tape cleanliness, how well it handles symbolic data, QFT alignment, how well it hits its target, life-MV balance in a specific task, its overall stability, and finally, its raw computational efficiency. The only ones that get to survive are the best all-around performers.
And this whole evolutionary process isn't just theory. The source material from Anthony Piper shows it's already produced some really promising configurations. So let's take a quick look at 3 examples of successful blueprints that have emerged.
First, there's the golden hex blueprint. This one is pretty fascinating because it evolved a 6-level logic that actually uses the unique math of the golden ratio. And what's the expected result? A system with really high stability and clean, predictable behavior.
Next up is ARC-7. This one uses a totally different, non-linear structure for its 7 logic levels. So instead of just pure stability, this architecture is designed to create really rich, dynamic behaviors. Well, that makes it a good fit for more complex and unpredictable kinds of tasks.
And finally, Synth Plus is just a perfect example of evolution doing its thing. It actually came from a mutation that added new, intermediate values to its logic, and the result is a system that's incredibly adaptive. It can adjust and perform really well on new things it's never seen before.
So these blueprints aren't just ideas on a whiteboard. There's a real, concrete plan to actually build and test these systems to turn all this theory into reality.
It's a methodical 7-day plan. On days 1 and 2, you start by seeding new populations with these promising blueprints and just run some quick tests.
Then, days 3 through 5 are all about tough stress tests. You start pulling out components to see how the systems hold up, and you really push them to their absolute limits. And finally, in the last 2 days, you analyze the top performers, you log their unique genetic codes, and you promote the best ones for much deeper study.
Okay, let's just step back for a second. We've gone through the logic, the operators, the evolution, these blueprints. What's the big picture here? What is the key takeaway from all of this?
At the end of the day, Phase N is really a search for a new kind of computational physics. It's a complete, well-thought-out framework for discovering controllable systems that aren't classical, but they're not really quantum in the way we think about it either. It's about evolving logic and these harmonic programs together to discover what comes next.
And that's our look at the Phase N architecture, which was authored by Anthony Piper. All content is copyright 2025 Anthony Piper, and all rights are reserved. For any permission or licensing inquiries, please use the contact information you see here.